So we will start revise simplex now. As I said, we'll just make a gentle introduction because there's something I want to give to you as a sort of a homework. It's not going to be graded, of course, but still you have to understand how this works to be able to, tackle with things to come in revise simplex. It's not going to take too much to start with, but as I said, you will see at the end of the course, at the end of the class, that you need to do something kind of a homework to be able to dive deeper into revise simplex anyways. So what's revise simplex? Before we start with revise simplex, we have to check out what we have seen so far, which is the simplex, the begin, the two-phase, and do simplex method. 4 different simplex types. Now, with simplex, it's about how we make iterations. It's about making iterations, okay? Begin and two-phase are how we deal with, greater than signs and constants, and how we make them ready for simplex. We just turn those, greater than signs into a ready form, into a standard form, ready form, applying simplex. With dual simplex, it's like using simplex, but for right-hand side values. How can we use simplex algorithm for negative right-hand side values? This is all dual simplex was about. So, we are going to apply simplex again, but in this form, it's going to be for bigger problems, if we can. Of course, we're going to start small, but we can apply this into bigger problems much easier. Now, the simplex itself isn't very robust for bigger problems. For example, think of a problem where there are, tens of thousands of constraints and thousands of variables. This is still a small problem. We can find problems with millions of constraints sometimes. So, tens of thousands of constraints, think about it. Just, try to apply simplex to it by hand, or even with a computer. You have to do lots and lots of iterations, and in all those iterations, you have to change lots of values, okay? Although it's simple mathematics, it's just summing or dividing or subtracting or multiplying the 4 operations, simple mathematics, it's still going to take a lot of time on the computer. With large enough models, it may take even hours, maybe days, depending on how you apply those, okay? With simplex, it's hard to calculate everything. With revise simplex, we are gonna take the calculation time and reduce it a lot most of the time. We'll see how that happens when we're talking about it. But still, as you can see in the second paragraph, it says, some coefficients in rows are not necessary to make iterations. We don't need to use them or calculate them at all. But we calculate them because we need to see the table in the next iteration so that we can use them later on if we need them. But with revise simplex, you can find a better way of calculating those values when you need them. As long as you don't need them, you don't calculate them. You only calculate them when you need them. So you just get rid of those, unnecessary values. You don't use them till you need them. You will see how that happens later on. So some of them are really important. Some values are important. Non-basic variable coefficients in row 0. Yeah, we need to know these values. Coefficients of the entering variable. Yeah, that's important as well. And the right-hand side values. We constantly use all of them. We use them for pivoting. We use them for finding out which non-basic variable is going to enter the solution, which basic variable is going to exit the solution. So if you can think about it, for example, in this table, let's say that this is a maximization problem. Let's go to maximization problem. Forget about the minuses over here. So we have x2 entering the solution. So this part is important for us. Yes, we have these values. This is important because this is a non-zero value. These are not important because we know that they are 0 anyway, so we will not need to calculate them because they are 0 right now. And these are the important values as well. Okay, this isn't that important, not as much as these values, but still we need to find the right-hand side value at the end to find the optimal value. Now, in this table, we have 1, 2, 3, 4, 5, 6 values that are important. The rest of them aren't that important to do the pivot. Okay? When we're making a pivot, we're just going to say, okay, this is, let's assume that this last one is that. We're going to make the ratio 4 over 2, 6 over 1. Okay, this is the pivot point. which has a less ratio. So we're just gonna use that one and turn it into 1 and get rid of the values up and down. So we will get rid of these values, and we will be making changes over here so that we can see what values we get at the end. For example, if x2 enters, e1 will leave. And we will have this one will revert to 1, and this will become 2. And in here, 1 and 1, we're just gonna get rid of this one and turn it into 0. So we'll just take this row and subtract it from here, and this one will become 4. Now, for the next iteration, we know that x2 is equal to 2 and e2 is equal to 4. We know the right-hand side once again. And now we will just start calculating the next iteration, the next table, if we need to. So this is just a simple way of showing how reverse simplex will work. But still, we need those values. We need to know those values. So we need to understand how they come into being. Now, this is the important part. Not that important, but still one of the important parts. Let's say that. Okay, this is the matrix form. The matrix form is the bread and butter here. We use the matrix form for everything here, from calculating the right-hand side values to making iterations to finding the objective function value when it's optimal, etc. We need to be able to show everything in a matrix form. Okay. Any model can be represented in matrix form, okay? But in any given iteration, we have basic and non-basic variables. Correct. These were non-basic variables, these were basic variables in this model. Number of basic variables is always equal to number of constraints. True. So we have this one was non-basic variable, by the way, but still these two are basic variables. So we had 2 basic variables and 3 non-basic variables, and these 2 basic variables had 2 constants associated with them. Yes. Each iteration was a basic variable, there's a living variable. In this one, from here, we knew that E1 was leaving the basis, so it was leaving the optimal solution, the solution, not the optimal solution, it was leaving the solution, and x2 was entering. So there's a basic variable that is removed from the solution at each iteration, and a non-basic variable that comes into it, something we already know. And if there are n variables, doesn't matter x, s, e, or a, and m constraints. Now, n variables and m constraints, there are amount of n possible solution sets. There are lots of solution sets. Any constraint can be, about any variable, so there are lots of different possible solution sets in there. Okay, and we have to find which one is the optimal solution. Okay, there are lots of different solutions, and there are lots of different possible, let's say, ways of finding those solutions. Let me just show you some simple stuff. For example, let's say that for the sake of simplicity, there are 2 constraints, and associated with those constraints are 3 points. I will ignore this one. This is the origin point. Yeah, it might be a possible solution, but still, it's the origin point. It's the start point dynamics. So we have 2 different, let's say, variables over here, and then we have s1 and s2 for those 2, x1 and x2 for those 2. We have a total of 4 possible variables that can be either basic or non-basic. We have only 2 constraints. Now, this one over here is actually a very large number. It's going to give us 6. We don't have 6 points over here. We have only, with this one, 4, right? No. We actually have a point over here and a point over here as well. Now, this is the feasible region we know. These still are candidates, but they're not feasible regions, so they cannot be the optimal solution points. But still, these are candidates. So there are 6 different candidates for optimal solution. We don't know which one is in the feasible region yet. We cannot know this. We just know the number. Okay, we know this for this situation, of course, because this is just a 2D representation. It's simple enough. But think about again thousands of variables. Yeah, we have that many solutions possible. So from here, from these 6 points, okay, we're gonna have to pick and find the best solution. Okay. How can we do that? Well, matrix form will be extremely helpful for that one. You will see step by step. First, change the model into a matrix. How do we do that? We have a simple model. Max z is equal to cx. C is the coefficient for your objective function, the C value. We will always use that C notation, and it's going to be a great C in that. We will see a capital C, but still, we have Cx. Of course, there's summation in there as well. And now we have subject to the constraint Ax is equal to B. Now, X is of course our decision variables, and A is constraints, coefficients of the constraints. So, with B being the right hand side. Now, this is the simplest form. We can just note that, say that C is a vector. Okay? For example, think about this. Okay, start with this one. We already know that Z is equal to Cx. The C here is equal to 1 and 2. Right? This is a vector. The coefficients are 1 and 2. Vector form. And for A, over here, for A, we will have 1, 2, minus 2, 1, 1 and minus 1 for this model. So, these are the matrices or the vectors, A and C. And for B, of course, we have 4 and 6. B is equal to 4 and 6 in this model. Now, this form isn't enough. We have to dig deeper. We have to go deeper and we have to, let's say, use more than one matrix to show A and C values, okay? Or more than one vector in case of C, of course. We have to divide them into two classes, okay? The objective function coefficients of non-basic variables and of basic variables. Now, this is important because when we, let's say, divide them, we actually classify them, and we can use that classification to be able to make iterations. That's why we need them. We will see in a second. But still, think about it. We have an x value, x vector. This is just the decision variables. So we actually have x is equal to x is equal to x1 and x2. So when you multiply C with x, you get 1x1 plus 2x2 over here. Or when you multiply A with x, you get 1, we actually have x3, right? 3 of them actually. So this is actually 1, 2, 0. 3 the same variables over here. So 1, 2, 0. And you actually have 0 and 0 here as well for x1 and x2 or e1 and e2. You actually have more zeros over here. 0 and 0 goes on like this one because you need to have values of E1 and E2 as well. This is X3, this is E1 and this is E2. So X3, E1 and E2 have 0 values. We only have values for X1 and X2. So when you multiply this X, and again you need to show E1 and E2 in here as well, because these are all your variables. And when you multiply these two, you actually get this formula, this objective function. Okay? And over here, when you take this into standard form, you actually have minus E1 and minus E2 is equal to 6 and is equal to 4. So these values are actually here as well. Okay? So when you write this one, you can also write it like this. Alright? So when you multiply A with x, you get the standard form for your constraints. Not the standard form yet, of course, you have to change it, but still, you get my meaning. You can find this part by multiplying A and x. So this shows over here. Now, when you multiply C and x, you get the objective function. When you multiply A and x, you get the constraints. Okay, simple enough so far. Now, we have the original model. how do we find an optimal solution from the original model? Now, the original model is z is equal to cx and ax is equal to b. Now, we will just take these apart, the c values and a value apart, and make them dependent on the basic and non-basic variables, as you can see on the right-hand side of the slide. Now, we will just say that maximum of z, maximizing z, is equal to cb times xb. Now, this says that take your basic variables and multiply them with their own constraints only. And take your non-basic variables cn times xn and multiply them with their own constraints only. Again, you get the same thing. This is the same as c times x. It's going to give you the same solution, but it's going to give you an ordered solution. The basic variables will be on one side, and then after that plus non-basic variables. Now, this form is the same as cx or ax is equal to b. Z is equal to cx and ax is equal to b. Same thing. And then the constraints do the same thing. B, which is the constraint coefficients of basic variables, times xb plus n times xn is equal to b. We're just, dividing those two matrices, C, which is a vector, and N. Okay? Just dividing them into two parts, basic variables and non-basic variables. Now, from here, we know that when you have an optimal solution, in your optimal solution, your constraints for your basic variables, your CB values should be 0. Okay? Because in the optimal solution, your basic variables will be part of the identity matrix and there will be no values on the coefficients, in the coefficient row for the objective function, which is going to be 0. There are no values in there. So, from here, we have to find a starting table. We have also other stuff we can check out. But, now, let's do this on the sorun mu? Now, we know the optimality conditions, so we're just going to have to find out how they work. Now, think about let's just write those. Now, let's start with the constraint part. Let's assume that I have picked basic variables as the optimal solution basic variables, okay? Now, you can have lots of different sets for basic variables, okay? For example, let's say that we have these 4 variables. And let's say that at the end of the solution, when we use the simplex, we find out that x1 and s1 are inside the objective function. They are the basic variables. And this is an optimal solution. Okay. Now, x1 and s1 give us the optimal solution. But at some point, even at the start, we can have s1 and s2 as basic variables. This is how we start all the time. S1 and S2 are in the solution, and they give us the current solution, not the optimal solution. From here, we make iterations to get over here, right? We start with S1 and S2, we make iterations, x1 enters, S2 leaves at some point, for example, and we get this one as the objective function's optimal, solution, optimal value. Nice. But in here, we have S1 and S2 as basic variables. So, when we are talking about basic variables, xb, we can be talking about any one of these. Okay? So, it might be those, for example, x1, x2, x1, s1, x1, s2, x2, s1, x2, s2, s1, s2. 6 of them. There are 6 different set for basic variables. This can be basic variable, these two can be basic variables, these two can be basic variables, these two can be basic variables. They each give us a different point. Okay, remember the. So 1, 2, 3, 4, 5, 6. For example, S1 and S2 is this one, where the solution is 0 and 0. Okay, these all are different solutions. Right, might happen. So, any one of those, okay, can be the solution. Alright. So, how do I find this one? Well, normally we make iterations. But here, we have to find the matrix one. And I say that when there is in any iteration, when there is an xb over here, okay, then there is an xb over here in the constraints. What are my coefficients for the xp? Do you remember that one? I keep saying it all the time. What is this value? What is the coefficients for the basic variables in the constraints? They're always the same. They always have to be the same matrix. I keep saying identity matrix. Identity matrix. So this has to be identity matrix. Okay? But it's not. It's the B matrix right now. So I have to switch this into the identity matrix. Okay? To be able to see. At the start, this is the identity matrix. I know with S1 and S2, it's always the identity matrix at the start. But when I make iteration, it has to stay the identity matrix as XP changes. These will change. XP will change. Keep changing. It's S1 and S2 at start, it will be X1 and S2 maybe. Then it will be X1 and X2. I don't know. But the coefficients should always be the same. So I have to change this form. All I have to do is just multiply this with the inverse of B from the left side, so that I can get rid of that B and identity matrix comes into play. So when I multiply everything here with the inverse of B, I get XB, which is an identity matrix here. I don't need to write this one, but still easy to remember. B minus B inverse N, Xn, is equal to B inverse B. Now, what does this give me? For example, when I have this, I can find values for all basic variables. It's a powerful tool. Think about it. If I know their B value, their coefficients, okay, in the starting table, I can just use the inverse of this B value, find right-hand side values in the starting model, and find a solution over here. This is very powerful. It's a very, very powerful tool. You will see next week better, but still, we have to understand this. By using this, I don't need to make any calculations at all. Okay, with the table. I can just multiply these two values and say that, okay, these values are the values for x. Why? Because, for example, I'm looking for x1 and x2. What happens if x1 and x2 in the solution together? Is it optimal? I don't know. I can check. I can just find the b values for x1 and x2 because I'm assuming that x1 and x2 are basic variables, and I have to check the initial table, the coefficients for x1 and x2 in the initial table. All of these values are from the initial table, always. Okay, but their calculations give us the table at the step at the iteration where these values are basic variables. Okay. The B, the N, the CB, the CN, they are always from the initial table, the initial model, but the multiplication over here, B inverse times B, B inverse times N, they are always from the iteration where those two are the basic variables. So, I can say that, what happens if x1 and x2 are basic variables? Well, all I have to do is just multiply them, that B minus value with the B value, and I will find out the x1 and x2 values. I don't know if they are optimal or not yet, but I will get there in the end. Still, this is a very powerful tool. So, this one always works, okay? And this is true for the optimal solution as well. Okay? In all iterations, we can check this one, and in the optimal solution, it's just going to give us the values for those basic variables. Okay? I don't need to even calculate this one. I don't need this one. Not yet, anyways. So, this is how the constraints behave. Okay? What about the objective function? Now, this one can be written like this: z minus cb xb minus cn xn. Now, what about the z or the objective function. What do I know about the objective function? What happens to, let's say, what happens to the coefficients of, let's say, the basic variables in the objective function? They're all zeros. Yeah, they're all zeros. So this actually should be a 0. So I shouldn't have xb in here. Alright, then I should get rid of xb. I cannot just, multiply or divide by something to get rid of xb, but I can change xb into xn using this one. So I can just say that, okay, xb is equal to b minus times b minus b minus and xn. Right? Because this equality holds all the way. So I can just take this one and put it over here. I don't need to see this one. As I said, it's the identity matrix. It's going to give xb anyways. So this equation holds. So instead of xb, I can write this one, which will transform my objective function into cb, minus cb. So b minus b minus b minus xn minus cn is equal to 0. Still not done. I'm just going to distribute this cb inside and then take this over to the right hand side so that I can get a better look over here. Z. Now, there is minus and minus, this becomes a plus, and there is xn and xn here, so I can write it in the form, of xn plus xn. I will just write cb times b minus n minus cn is equal to cb b minus b. Now, this is my objective function at all times, depending on how I choose my basic variables, and these are my constraints, depending on how I choose my basic variables. So, as you can see here, I can just calculate my z value instantly, depending on how I choose my basic variables. So, if I choose my basic variables as x1 and x2, all I have to do is just find the cb for x1 and x2, multiply it by the b inverse of x1 and x2, and multiply it by the right hand side value. That's all. And I will have my objective function value when x1 and x2 are in the solution. Now, as I said, there are 6 points. I can try all those 6 points and find out which has a greater z value, and I'll be done with it. Of course, this is not efficient for bigger problems, but this is a way I can do. Instead of making all those iterations, I can just calculate all those cb and b minus values, which is not easy even in a 2 variable situation, but still, this is something I can do now. I have that power now. I don't need to deal with simplex anymore. This gives me that power. Okay, cb, b minus 1b. I can find all the z values and I'll find out which one is the greatest one, and I said, okay, this has to be optimal, which is not correct all the time, because as I said, we can be outside the feasible region, like some feasible regions here. I can find one of these 2 points as the optimal solution, but still I can find those points. This is the important point. So I can make iterations. To check optimality, I can just take a look over here. Is this optimal? I don't know if it's optimal. Let's check. How do I check this one? If this is a maximization, all these values should be greater than 0. As long as they are greater than 0, it should be optimal. Why? Because they are the objective function coefficients. Take a look over xn times this one. These are the non-basic variables, so if the coefficients of non-basic variables are greater than 0, then they're optimal. Because the non-basic variables, they have a coefficient of 0 anyway, because the non-basic variables are not even in here. Okay? So, this part is to check optimality. This part is to find the right-hand side value, the z value. This part is to find the basic variables, the value of basic variables. So I can use those 3, let's call them equations, functions, whatever, those 3 parts to find the values that I need all the time. Okay. This, as I said, is optimality, and you can see in the, slides anyway. It's optimality, it's the right-hand side for the objective function, and these are the constant values. Now, from here, we can just take these and make them into a simpler form to be able to show them, as you can see in the table form over here. The z value is always 1 for the objective function, of course, and always 0 for the coefficients, constraints. And xp is always 0 for the objective function and always identity matrix for the constraints. And xn, which is the important part, the non-basic variables, have this cb times b inverse times n minus cn value for the coefficients in the objective function, and b minus b inverse times n for the constraints. And right-hand side values, as we have seen over here, they are the same. Now, what I want you to do for next week, I want you to derive these, make these operations yourself until you get them without looking at the book or the slides or anything else. Start with the simple form, multiply it or get it bigger. Okay, start with the simple form, which is c times x, subject to ax is equal to b. Then revert to this form and then make your operations and until you find these two values. It's going to take about half a page or maybe a page depending on how you write, but still, you have to make sure you can understand how that goes to be able to understand what happens next. Okay, it's the important part. So, till next week, get these two values, these two functions, these two equalities yourself. Okay, derive them from the starting point and understand what they are. If anything, take the Dakota example and use those values and calculate the optimal solution yourself. Check out which ones are the basic variables and then calculate the optimal solution for the Dakota yourself, or the Gepetto, or whatever you want to, any of the models we have seen so far. Just make sure that you understand how these work. If you get that, then the rest of this subject will be easy. Okay? So please just take those, find those, derive those from the start, and use Dakota or whatever you want, whatever model you want, to find the optimal solution without making any iterations. You don't need to make any iterations. Okay? As I said, these values, the xp is of course the basic variable set, but still, the b minus, the n, they all can be found in the let's say table, in the initial table, or even in the model itself. For example, let's just make an example once again. Let's clear this part so that you know what I'm talking about. And write a simple model. Max is equal to 5x1 plus 2x plus 3x3, subject to 2x1 plus 3x2 minus 4x3 less than equal to 10, and x1 minus 2x2 plus 3x3 less than equal to 12. For example, let's say that we have two constraints and three variables. We will have for the total x1, x2, x3, x1 and x2. These five as our x values, okay? And let's assume, we don't know yet, but let's assume, we are assuming right now. x1 and x2, these two are the basic variable sets. So the non-basic variable set is going to be x3, s1, s2. Now, with Dakota or with, Gepetto or another model, you already know the answer. You already know which of these variables are going to be basic variables at the end. So you can just pick those, 2 or 3 or whatever. But here I'm just picking randomly. Okay, I don't know the solution because it's a random model. So let's assume that this is the optimal solution. This is going to give me the optimal solution. Now, from here, I have to find the b value. Now, the b value is going to be the coefficients of x1 and x2. Which is going to be 2, 3, 1, minus 2. 2, 3, 1, minus 2. The n value is going to be coefficients for these guys over here. It's going to be minus 4, 3, 1, 0, 0, 1. Because S1 and S2 will be the starting identity matrix part anyway. So these are the n. And I need to calculate B minus, B inverse. I can just calculate it from here. if you remember the, shorthand for version of it. If I'm correct, I have to change signs and then divide them by the determinant. I'm not sure yet, but still, that was a shortcut for it. I don't remember it right now, but still, it's not that important because I can calculate this easily. Even if B is bigger for 3, for 4, for 5, you can calculate B inverse easily using, for example, Excel or MATLAB or any other thing you want, because this is not about calculating inverse of it, okay? Normally there are different ways, but still, when it's not right. So you can calculate the inverse of B over here. And then what I need to do is just find the CB and CM. For example, I need CB and CM. Well, CB, x1 and x2, 5 and 2. CM, x3, s1, s2, 3, 0, 0. I divided them. I found all the vectors and matrices I need. And then what I need to do is just find the values over here. So I will just find CB times B inverse times B. So this times, I need to write B as well. 10 and 12. So CB, B minus, and B. I'll just multiply these three vectors, matrices, whatever. And then I can find the Z value. And I can find B minus times B as well, which is going to be this times this, which will give me the values for x1 and x2. And I can find over here this optimal condition values, the objective function values for non-basic variables, which is going to be a bit harder to calculate because there are 4 different vectors in here or matrices in here now, but still it can be calculated this times this. So CB times B inverse times N, this times this, and I'll subtract CM from them, which is this one, and I'll find values. So I can just find any solution. They might be optimal or not. I will have to check this one if they are optimal or not, and I will have to check this one if they are feasible. They can be infeasible as well. Okay. So after checking those values, I can just say, okay, it's optimal, or no, it's not optimal, I have to keep going. But this is for next week, okay? The optimal solution, is it optimal or not? How do we keep making iterations? Because there are iterations with as well if you want to. This is not all about finding a solution at a certain point, but it's about making iterations anyways. So the iteration making part is for next week, but for the homework, for your, let's say, practice, I want you to find the solution to something you know you already know, to a model you already know, by using this one, okay, this form. If you can do that, then you have understood how this, revised simplex works at a fundamental way, okay? And then you can understand it further next week, because it's gonna get harder next week. This is the easiest part with revised simplex. All right? Any questions? All right, then see you next week, I would say.